Okay, so let's finish up the naive Bayes. So first thing that I want to talk about is the connection of naive Bayes. Naive Bayes and the logistic regressions. So in order to have a fair comparison, I'm going to assume all the features are discrete and have a k-states. So basically all these x of d, this all have the k-state from 1 to the k. And also I'm going to define this my xdk. So this xd has an k-state. I'm going to define xdk as an indicating function that if xd is equal to k, that will be 1. If xdk is not, xd is not equal to k, that will be 0. So this is basically xd itself is a 1/2 vector. Of feature d, but it actually has a dimension of k, right? So then in these cases, my conditional and a conditional probability is given as follows. The probability x conditional on y equal to c, and the theta is basically I need to multiply all possible d from 1 to capital D of this categorical distributions of xd conditional on y equal to c and theta. So this is actually giving as multiplications of d from 1 to the capital D, multiplications of k from 1 to the capital K, and the theta d c k power of xdk. Okay, so this is so additional so like this is basically how we express out the categorical distributions, and we multiply this categorical distributions from d from 1 to the capital D. All right, so the posterior distributions is probability y equal to c, conditional on x and theta. It is so, and also, but in this cases we need to add on this and the prior. So the prior, which is probability of my x. Wait, is it? Is it right? Sorry, the y equal to c. And the pi, I'm going to call it pi c here. Okay, so this is just and very similar to what we already did in the lecture, and also very similar to the homework that you're going to do as well. So this posterior, interior distribution is basically pi c multiplications of d. I'm going to simplify this notations a little bit. Theta dck and the xdk, and it divided by the normalizations for all possible c's. C prime, pi C prime. So this pi is actually it's parameter. This pi is multiplications. Yes. So product. So this is fundamentally like, two different things. Don't get confused here. So this is big product of D, big product of K, theta D C prime K, X D K. So this is the posterior, distributions. So and probably have seen something. This before. I'm going to and rewrite things a little bit. So this becomes as following. That is exponential of the logarithm of pi C plus summation of D, summation of K, and xdk of logarithm of theta dck. Then, so the bottom is the summation of the C prime of exponential of log and the log pi, and this pi is the variable C prime plus summation of D, summation of K, xdk, log of theta dc prime K. Okay, so I'm going to rewrite things a little bit. And you can rewrite things and vectorize it, and it becomes the following. So this becomes exponential of, this is going to be, I'm going to call this gamma of C plus, I'm going to rethink everything. So right here as D and K. So so we treat D and K right here as being, and combine the index. So basically X right here, and I want this to be a whole vector. So basically I'm going to say X right here is X and dk. This D is from 1 to the D, and K is from 1 to the K. Okay, so this is basically we and vectorize this D and K. And this becomes, I can just rewrite this to be beta of C transpose of X. So you can do similar things on the bottom for the C prime of exponential of gamma C prime plus beta C prime transpose of X. So here, this gamma C right here is log of pi and the log of pi C. This beta C is actually a vector right here. Is I'm going to vectorize the log of theta dck, where the D is 1 to the D and K is 1 to the K. So vectorize the both index of the D and K. So this, what you got is exactly the multinomial and the logistic regressions with the soft and with the softmax output. So, and you can see this right here. It's a linear model. After linear model, you are going to output this as a softmax. So this is multinomial. And the logistic regressions. With the softmax. So you can actually compare the result with what we have talked about on the logistic regressions. So here we assume, and this is a discrete, has a k state. And actually this result holds for other like feature distributions as far as it is in exponential families. So this actually holds for arbitrary feature distributions for in exponential family. For example, if you want to work with the Gaussians, if my feature distribution is a Gaussian, this is still work. Okay. So actually, this posterior distribution is precisely what we already trying to work out. The logistic regressions with a softmax output, but differences is in naive Bayes. So we are trying to maximize the joint log likelihood. The joint likelihood. Right, so we have and spend quite a bit of time to justify. We're trying to maximize this like likelihood, and the d here is x and x of the y, and you and include everything at the same time. So this is joint, and the likelihood is probability of d given theta, which in this case is multiplications from I from 1 to the n of p of x of I and y of x of I and the theta. But in logistic regressions, we're actually not maximize the joint likelihood. We are maximize the conditional likelihood. So what is that is we're trying to maximize the so yi I from 1 to the n conditional on x of I from 1 to the n and the theta. All right, so this is equal to multiplications of I from 1 to the n of probability of x of I, y of I mx of I and the thetas. So, and you can see this is give you, so that's why both of that actually give you different results. But of course, if we use this naive Bayes and actually and trying to look at everything in terms of and the posterior distributions, this actually goes back to the and the logistic regressions. But in general, this actually, will give you different results. So that's why both usually give different results. So you can see this, and these two models, although looks sometimes similar, sometimes different, but fundamental differences is the objective is different. The objective that in naive Bayes is joint likelihood. In the logistic regressions, that will be conditional likelihood. So what is the differences in general? It's actually lies in these two framework. The one is called the generative classifier. One is discriminative and a classifier. So these are the two, and these are the two pictures right here. For example, this is something called generative and a classifier. So the generative classifiers is we directly model a form of P of XY. That i.e. I have prior, I have a conditional probabilities. So that means we can use each of the class of Y to generate the sample of X if we want, since we know the joint distributions. And when we're trying to fit, we're just trying to maximize the and joint likelihood, like what we did on the naive Bayes. There are other two parts that we're going to cover, which is LDA and QDA and the Gaussian mixtures. Both are generative classifier. So basically, we're trying to maximize the joint likelihood. We're not going to talk about variation autoencoder in this course, and we're not talking about GAN in these courses. So you can see right here, if we work with exponential family here, in naive Bayes, we just class and fit this and classify by just counting and averaging, right? So this is fairly straightforward. We don't need to solve a convex or non-convex optimizations numerically, which could be time consuming, but in a naive Bayes, all we need to do is just to do some simple countings. That's really easy to fit. If the distribution is happen to be an exponential family, usually some and the Gaussians, and then the mean and the variance will be sufficient. And also, and this whole thing can handle the missing input features very well. And what does that? And we're going to talk about in detail in the next and momentarily. But in the other right here for the discriminative, we're going to talk about this as well. We always assume this feature is available and to be conditional on. If we have in a situation that X feature is missing or part of the X is missing, that we can't even trying to make the predictions. And also, for the generative classifier can handle the unlabeled training data well. For example, you have and you have some data is and labeled, or some data is not labeled. It is not natural or very hard to process in the discriminative classifier. So this setting is called semi-supervised learning. So semi-supervised learning is something I didn't talk about, but this I mean practice is like very, very popular. You will see this kind of situation all the time. That means we have some labeled data, we have some unlabeled data. Okay, so can we using the information that we have on the labeled data to make any further prediction for those unlabeled data, right? So this is how you and how this is being processed. But in general, if you want to work with discriminative classifier, that would be and tensor almost impossible because that and the discriminative like classifier, when we do the training, they require the yi has to be like observed. If yi is not observed, then we can't do any training here. And also we can estimate the parameter of each class conditional densities completely independent. So so that means if we add more data here, we don't actually need to retrain these models, right? So and we can just like and recount and a lot of other and a part can be just re-estimated separately and with very minor modifications. If we so in the discriminative classifier, that's not going to happen. So the whole model has to be completely retrained. On the other hand, the discriminative and a classifier is basically the cases that we're trying to maximize the conditional probability. So this is basically we're trying to maximize the probability of y conditional on x and the theta right here. So this can be used to discriminative. So between like different classes, could be like binary, could be multi-class. You have a multiple example, for example, k nearest neighbor, logistic regression, SVM, decision trees. We are not going to talk about k nearest neighbor. We just briefly mentioned that in the first week, but this is like very, very straightforward. Everyone should know that. For the rest of the part, we're going to talk, and we have to talk about, logistic regression. We have to talk about SVM. In like today's lecture, we're going to talk about decision trees. We are not going to talk about the random forest in this course. It will be taught in 593, but just give you a heads up on and what will be covered here. So an advantage of this discriminative classifier, it's often much accurate than generic classifier. The reason is, the conditional and the distribution is often much simpler, and therefore that will be much easier to learn. For example, it could be a sigmoid and the distributions, and it could be a and the softmax output. And the softmax distributions. So in general, that will be much simpler and to be learned than the joint distributions. And this joint distributions, it's multiplications of the prior and the conditional distributions. And of course both of that, and this will be much more complicated in general. And also, this discriminative models do not need to waste effort on modeling the distributions of the input features, because and right here, and we need to, if we want to calculate this joint distributions, that means we need to and build the models for the input features, which is a probability of and a px right here. But usually that will be quite and quite tricky sometimes, but and it might not be and super accurate. So that's why if we're trying to use discriminative models, then there's no need to waste the effort to model this type of p of x right here. Distribution of input feature, this will be p of x. And this can handle this, and another big advantage is this can allow us to pre-process the input arbitrary ways. So that means we can try and perform the polynomial expansion of the features. It will be harder to define and the generative models for such pre-processed data, because new feature can be very much correlated in a very complicated way, which is very hard to model for this, distributions of the input features. Another an advantage is, and we have a well-calibrated probabilities. So for example, this naive Bayes and classifier, we have very strong, independent assumptions. That means each feature conditional on the labels are independent, which is often not true. And this is very way too optimistic or way too simplified and assumptions. But on the discriminative model, such that and the logistic regressions are often better calibrated, we don't have to make such simple or such strong assumptions, and turns out that we can have a better probabilistic estimate for the logistic regressions. But by the end, if you have some missing data, this is something I haven't talked about in the past, but in practice, this turns out to be extremely important. In generative and a classifier, we can handle this situation by marginalize out these missing values. So we can marginalize and marginalize the missing values. So what does that actually means? For example, if we have a feature of x, which is x1 to xd, but the first one, x1, is missing. So we can compute. So basically, and we can still do all these kind of calculation that y and y equal to c, conditional on x2 to the d. Let's do it d here, right? And the theta. So this is posterior distributions. That is proportional to probability y equal to c and probability x2 to the d, conditional on y equal to c and theta. And what you can do is you can, so this is basically y equal to c condition on pi, probability y equal to c condition on pi. You actually summation x of 1 and modulus of all the possible x of 1, that you have 1 to the d, condition on y equal to c, and the thetas. So this go back to this conditional probabilities that we actually asked for. Okay, so so in naive Bayes, naive Bayes, in fact, you can just and literally calculate out explicitly. So the summation of x1 of probability x1, x2 to the d, conditional on y equal to c, and theta. In fact, we can factor out that because we know conditional on y equal to c, in naive Bayes, the feature x1 and every other features are independent. So, and basically I can separate this out. So this becomes summation of x1 of probability of x1 conditional on y equal to c and theta multiply x2 to the d, condition of y equal to c, and theta. And we can actually do this summation right here first by factor out the rest of part. This is basically summation all possible of x1. This is just give you 1. This is equal to probability of just x2 to the d, given y equal to c and theta. So we just simply filter out, this missing features, and we don't need to worry about x1 at all. This is just being perfectly modeled by x2 to the d's, right? So this is very straightforward. And in naive Bayes, this can handle these missing features very naturally. If you work with other and generative models, you actually have to calculate, this part sometimes can be done analytically, sometimes can be done with the numerical simulations and by simulations. So, so this actually depends on the problem settings. All right, so that's all for the naive Bayes part. That's the first part of today's lecture.